Welcome to Understanding Wildfire with Professor Monks. Today's topic, How Fire Burns, Part 1. The ancient Greeks believed that fire was one of the four elements that made up the world, along with earth, air, and water. Various early philosophers argued over which of the four elements was the most fundamental, including Anaximander, who made the case that everything is ultimately made from fire. You may be familiar with the idea of the four classical elements if you're a fan of Avatar: The Last Airbender, or, from my generation, Captain Planet. In ancient China, fire was considered one of the five elements, along with earth, water, metal, and wood. If you look at a modern periodic table used by scientists all over the world today, you'll see over 100 elements, but fire is not one of them. That's because we now know fire isn't an element at all. Fire is a process. Specifically, we can define fire as a rapid exothermic oxidizing reaction. Now that's a lot of big chemistry words, so let's break it down. First, fire is exothermic. That's exo meaning outside plus thermic meaning heat. In other words, fire is a process that releases heat. It creates more energy than it consumes. That's why we light a fire to stay warm, to light up a dark night, or to cook food. The engine in your car uses fire to burn gasoline, generating the energy to drive places. And power plants that burn coal, oil, natural gas, or biomass work on the same principle. Here's what happens when a fire burns on a chemical level. Fire takes in oxygen from the air and combines that with some sort of fuel. The most common fuel is what we call carbohydrates. That is, molecules made out of carbon and hydrogen. Living things are mostly made out of carbohydrates, so fires easily burn fuels like wood or grass. So that's oxygen, carbon, and hydrogen going in. The reaction then produces water, made of hydrogen and oxygen, and carbon dioxide, made of carbon and oxygen, as well as energy. That's the exothermic part. So like a good chemical equation, this one is balanced. The same elements go in as come out. We call fire an oxidizing reaction because it uses pure oxygen, usually coming from the air, as one of its inputs. Then it puts out several compounds that contain oxygen. The pure oxygen got combined with other things. There are many types of oxidizing reactions in our world. Fire is just one of them. For example, rust is the result of an oxidizing reaction. Oxygen from the air combines with iron in some object to produce the compound iron oxide, with its distinctive orange-red color. Another important oxidizing reaction is digestion. Your body breathes in oxygen, then combines it with the chemicals in the food you ate, producing, among other things, carbon dioxide, which you breathe out, and energy to keep you going. Now, a reaction that takes in oxygen and carbohydrates and produces carbon dioxide and energy. That should sound familiar. In fact, the chemical formula for fire is essentially the same as the chemical formula for digestion. So that brings us to the third element of our definition of fire. It's rapid. Fire does basically the same thing as digestion, but it does it much faster. That's why fire gives off such bright, intense energy, but also needs to be fed continuously. One more thing to note here is that the chemical formula for fire or digestion is basically the opposite of the formula for photosynthesis. Plants take in water, carbon dioxide, and energy from the sun and produce carbohydrates and oxygen. Photosynthesis, digestion, photosynthesis, digestion. It's the circle of life. And that's going to be very important as we learn more about fire. The growth of plants through photosynthesis and their consumption by fire and digestion balance each other out. But wait, you might be saying, when something burns, I can see the fire. It certainly seems like there's a thing there. Well, what you're seeing are flames. The actual burning is occurring at the surface of the fuel. But that burning is giving off a variety of gases, components of the fuel which don't burn, but which do vaporize at the temperature of the fire. Those gases are floating up from the fuel, and they're so hot that they glow. So flames are glowing hot gases given off by the chemical reaction that is fire. If our fuel is pure, it will get consumed completely by the reaction if the fire burns long enough. But most natural fuels, like wood and leaves, are full of other chemical compounds. Some of these turn into gases because of the heat of the fire and float away with the smoke. Others are left behind as solid ash. So we know what fire is, a rapid exothermic oxidizing reaction. But when and where will it happen? We can summarize the factors that enable fire to burn with a model called the fire triangle. The fire triangle has 3 legs, each of which is necessary for a fire to burn. The first leg is fuel. We need something for the fire to consume. That fuel could be living plants like trees and grasses. It could be dead plants like fallen leaves and dry logs. It could be things constructed by people, like wooden houses. Or it could be fossil fuels, like coal, oil, and natural gas. Second, we need oxygen. If your fire is burning outside, there's plenty of oxygen all around us. In fact, the Earth's atmosphere is about 21% oxygen. But sometimes you want to get a fire really charged up by blasting it with extra oxygen. You can do that by blowing into the base of a campfire or using a bellows in a blacksmith shop. Engines that burn things in a confined space need special equipment to ensure the oxygen supply. And third, we need heat. Now, we know fire is exothermic. It gives off more energy than it takes in. But you still need a bit of energy to get things going. Otherwise, all of our forests, which are made of fuel and surrounded by an atmosphere full of oxygen, would just spontaneously burst into flame at any time. You need that initial spark to get the fire going. Once a fire is burning, it will keep going if the energy produced by burning one piece of fuel is enough to get the next piece of fuel started. A fire needs all three legs of the fire triangle to keep going. Take away one leg and the fire goes out. That's easy to see with fuel. If you stop feeding your campfire, it will eventually burn itself out. Firefighters will often clear a fire line, a strip of land where all the fuel is removed, in order to stop the spread of a fire. Take away the oxygen, and your fire will also go out. That's the principle behind those bell-shaped candle snuffers. The snuffer keeps new oxygen from getting to the candle, while carbon dioxide builds up around it. Eventually, there's not enough oxygen, and the flame goes out. And finally, you can stop a fire by taking away the energy that keeps it going. If the energy from one piece of fuel burning isn't enough to get the next one going, the fire will stop. That's why water puts out fires, and why you basically never see fires burning underwater. On Earth, fire is a land-only phenomenon. It's also why dead, dry leaves and wood burn much more easily than living ones that have a lot of moisture in it. The way it works is this. The heat you have to get the fuel to in order to keep a fire going is greater than the boiling point of water. So before something can burn, you have to boil out all of the water. But boiling water takes a lot of energy. So that means it takes a lot of heat to keep a fire burning in wet fuel. Add some water and it becomes too much and the fire goes out.